Okay, good morning everyone. Normally we do the presentation first, but I want to get through a couple of things. So if you don't mind, can we do the presentation maybe in the last 20 minutes? Is that okay? Yeah. Okay, all right. Okay, so I want to get started on, another very important announcement is that so in next Tuesday's class, we will have a quiz, and it will be just an in-class quiz. It'll be for about 45 minutes, so it'll be a bit shorter than the midterm. So the midterm is actually the Tuesday following that, so not next week, but the following week, Tuesday, is the midterm exam. It will be also in this class. For those of you who are remote, you'll be doing it over Zoom. So I will send a Zoom link for the exam, and then the exam will be emailed to you at the start of the when the exam starts, which will be 8:15 more or less. So for those of you who are remote, you should have your cameras on, showing your face, and you should just basically do the exam, and then you should email it back at the end of the exam time, which is about 45 minutes, be announced on the day. For those of you who are here, then of course, so you'll hand in the exams just directly to me. So so that's the midterm, but the quiz will be in a way a kind of a mock-up of the mock exam of the midterm. So it will cover everything up until end of this chapter. So that's why I kind of want to get started on this one. So it'll cover everything in chapter 7, assuming I get through everything in today's lecture, and then we'll also have Thursday's lecture next week to basically finish off this chapter. Okay, so let's get started on this chapter, unless there's any questions. No. Okay. All right. So this is about kinetic energy and work. Okay. Sure. It doesn't work. Okay, now it works. Okay, so I think you're all familiar with the concept of energy. It's actually kind of pretty hard to define what it is, even though we all know what it is roughly. What actually is it? It's a little bit hard to define, but essentially it's a number that we assign to a particular configuration of a physical system. So you might imagine like these are two configurations of a gas in some container. Now basically, even though the configurations might be different, you can see this atom is going that way, that atom is going somewhere else. These are different configurations. They might have the same amount of energy. So it's some kind of, it's like some kind of scoring system that you are applying to physical states. So you are kind of assigning some number to it, and that it should tell you something about it. Now we could always make up any kind of scoring system and say that that state is worth this number, and that another state is worth another number, and so forth. But the value of this thing is that it's a quantity that is conserved, and I'm pretty sure you're probably sort of familiar with conservation of energy. You've at least heard it just in everyday language. But this is what makes it a kind of very useful concept, because it's even though it's some kind of a rather abstract kind of thing, you're assigning some number to some configuration, it's in the end it turns out to be something that's kind of conserved, so you can sort of exchange it between different configurations, people, as we'll see. So, at this point, you probably don't need me to tell you, an analogy of what energy is, because you perfectly know well. You know that, okay, I know what energy is. I don't need to give me an analogy of what energy is. But this analogy will help later on in understanding other concepts like work and how it relates to energy, because there's quite a few different concepts which all seem to be almost the same thing. They're all got the units of joules, and they all seem like energy of some form. But so just to have everything absolutely clear in our minds, I'm going to follow this kind of analogy later on. So I'm going to think of energy as something like a bank account, and energy is sort of money. It's like the analog of money. So we can sort of assign a particular number. So the analogy between energies is money. So this person has $1,000. This person has $5. This person has $4. In the same way, we can sort of say that this person, or it might not actually be a person, it might be like a object or some physical system. This person has like 1,000 joules of energy, or this thing has 5 joules of energy. That object has 4 units of 4 joules of energy. So this is the kind of analogy that we're going to be working with a little bit later on. And the conservation aspect that I was talking about, which we'll explore later, is that basically, the amount of money, unlike real money, which inflates, deflates, and what was worth $1 today might not be worth $1 tomorrow. But in this kind of ideal world, the money is kind of static. That's why I kind of use gold. Gold is sort of supposed to be this stable type of currency through the ages. So it's kind of intrinsic and doesn't kind of just disappear. Okay, so let's look at different a particular type of energy. We'll be talking about other types of energy later on, like potential energy and so forth. But in this chapter, we're mainly talking about, the kinetic energy. So you would probably seen this formula before, but kinetic energy is an energy associated with the movement of an object. So if something's moving, it has some energy, and there is a formula that gives this, and it's half mv squared, where m is the mass of the object, v is the velocity. So this is a way of converting basically something, a way of figuring out how much energy something has associated with the movement of the object, right? So I've always been a little bit puzzled by this formula. You sort of learn it in high school, but what's with the half, and what's with, why is it v squared, and sort of, it doesn't look like a super natural kind of formula. Well, firstly, certainly you need a kind of a squared here, because it doesn't have to be squared, I suppose, but it needs to be something that is independent of the sign of the object, because obviously if a particle is going that way or the opposite direction, it needs to have the same energy, or any other direction. So more generally, this is actually kind of a vector quantity, and so this v is the absolute. It's the, so if you've got a vector of v, it's v squared is really v dot v, right? So that it's independent of the actual direction of the object. Now it wouldn't have to be v squared. You could also have v4 or something like that. And then so you might wonder, why v squared? And what's with the half as well? And so basically, where this actually comes from, and this is not really part of the course, it's this kind of weird formula, because actually it's a approximation, really. So you think, okay, kinetic energy is half mv squared. It's actually not really. It's actually just the first order in the expansion of a more general relativistic formula. So we all have heard, E equals mc squared, right? That's actually just the mass of the energy associated with something that's not moving, right? So if you've got something that's just sitting there, it's not moving, it's got mass m, then actually that, in fact, contains, if you converted all that energy, using some, say, nuclear process, then the amount of energy in that is mc squared, which is actually usually a gigantic number. This is why atomic bombs are so powerful. Now the next order term in this formula is half mv squared, right? And so the reason why it's got this half and the reason why it's got this weird sort of factors, it's basically because it's actually just a term in the expansion, and it's not really actually the formula should be that, really. And so there are actually other higher order terms like mv4 over 8c squared, which you never really see. So actually this is also part of the kinetic energy, but it's just small because it's got this c, which is speed of light. Sorry, I forgot to mention that. So there's a c squared, and in fact there's, v6, va, it sort of goes forever. So actually, probably the really correct formula for kinetic energy should be this formula, but you subtract mc squared, which is just the rest energy, and then all that stuff is the kinetic energy. But it's a little bit of a complicated formula, so let's normally just go with half mv squared, and for any kind of velocities that are not like light speed, all these terms are very small anyway, because got c squared on the bottom. Okay, so let's now talk about work. So this is where we've got sort of another energy-like concept. So work is defined like in this gray box here. So work is the energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, energy transferred from the object is negative work. So, so the first thing that you kind of want to tune into here is that actually work is something that actually involves two parties, right? So work is transferred, it's transferred, right? So already if it's a transfer, of course that implies there has to be two things involved, a person, an object, maybe two objects. And so some energy is being transferred from one party to another. So work always involves kind of two objects, right? And there's this kind of phrase that you often use that, so if Bob is pushing this box here, so you would say that Bob is doing work on the box. And that phrase is implying that there is a transfer of energy. Basically, Bob is actually giving energy to the box, right? So, for example, like if you were to look at this case of Bob pushing this box, the kind of accounting that you might do in terms of energy is that Bob's complete energy store, I've just picked a big number here, he's got fat reserves, his body, all the energy that he could possibly expend from his body, from that moment. He's not going to eat anything anymore. All the energy that he could possibly expend is, let's say, some number like this, right? And by pushing the box, he's basically expended some of that energy and just given it to that box, right? So if you look at the energy of the box, and let's just forget about friction or anything like that, so it's frictionless. So then the box, say, if it's not moving at the beginning, it would speed up, it would start moving, sliding. Afterwards, it would have 100 joules. And then Bob would have given the box 100 joules, so his energy has gone down. So you can kind of see that this is where the sort of the bank account analogy kind of starts to sort of clarify things, if you like, at least. It sort of identifies what these quantities actually mean. So essentially, if you've got two people like here, they've got, this person's got $5, this person's got $4, and somebody's transferring money from one to another. Now, obviously, the money in this first person's account goes down, money in the second person's account goes up, right? So what we're calling work here that's the transfer, right? So before, when we were just talking about energy, that's just talking about, okay, so this person's got, $5 or 5 joules of energy, and this person's got 4 joules of energy, and there's no, there's no transfer or anything like that. We're just talking about the energy of each person. But if we're talking about work, it's always to do with the transfer. So that's basically the meaning of work in a physical sense, right? Okay. So how do we actually calculate the work? So according to the definition, it's energy transfer to or from an object. Okay, so I think we now understand that. So transfer of energy by means of a force, right? So there's a force involved, and the force is the mechanism of the energy transfer, right? Okay, so basically we can work out what the energy transfer is in terms of the actual force, and there's a kind of a neat little way of figuring this out. So we know, well, we can define force to be related to acceleration in this way. So F equals ma, as we know. Now, as I said, this is all frictionless, and let's say, okay, so in this case I've said that it starts from some initial velocity, right? Now, by Bob pushing on this thing, he's applying force, making it change its velocity, so it will have a different velocity at the end. And we know from second law that the acceleration is related to the force in this way. So we can write this equation instead of acceleration. We can write it in terms of force. So for example, so basically what we can say is that acceleration is force divided by mass. And so from this equation of the velocities here, we can eliminate acceleration and write it in terms of force. This. And if we just do a little bit of rearranging, this actually becomes a pretty clear formula. So just put V naught on the other side, and then just put this factor of 2m on the other side, then you would get half mv. Half mv, this difference is equal to force times distance. And we can interpret what this thing means, right? We've got a formula for the kinetic energy, and this is exactly kinetic energy, which is kind of amazing that it falls out of this formula in a way. So we can interpret this thing to be saying, okay, well, this first term is the final kinetic energy, the final kinetic energy, minus this is the initial kinetic energy. So this change in kinetic energy can actually be related to the force, and there's a nice simple formula of basically the work is the force times distance, right? So F times X. So if Bob is moving this thing through some distance d, okay, so I've used different variables here, maybe, okay, to be consistent, maybe I should have called this X, So if I'm moving this through X, then the amount of energy that he is transferring to that object is just the force times that distance. And that changes the kinetic energy of the system. If we go back to the sort of the definition box here, so energy transferred to the object is positive work, and energy transferred from the object is negative work. Okay, so let's, so basically this is our sort of, I'll just call it W. So that's work, right? So we can easily see from here how this thing could be potentially positive or negative, right? So if V naught is something small, the magnitude is small, and finally the V naught is large, right? Then of course this will be positive, right? So if this thing is positive, then of course it's speeding up, right? So speeding up, so you're giving it energy. So this is an instance of positive work because the energy is being transferred to it. So energy, this Bob is giving energy to the box, so it's increasing in energy, right? But we could also consider the opposite situation. So in the opposite situation, of course, so this thing could be negative if, say, actually the final velocity is actually slower than the initial velocity. In other words, it's being slowed down by Bob, right? So initially it was going pretty fast. Bob's pushing on it, and it kind of slows down. How this can happen, of course, is that instead of the initial velocity of this thing being just, say it's just sitting there, perhaps it's a different situation where we've got this flying box that's sliding across the room, and Bob is frantically trying to stop it from moving. So, that's the situation of this case, right? So Bob is trying to prevent or trying to get this box to come to a halt. So, of course, if you see a flying box coming towards you and you're trying to stop it, of course, you push it in the opposite direction, right? So in this case, the velocity is this way, force is this way, but say, this is a big heavy box and he's trying to stop it, but the box is too strong, and so he's pushing this way, but it's going backwards, right? In that case, the force is this way, but in fact, the eventual direction is backwards. So he's pushing it, but he's kind of not completely successful in stopping the box immediately, and he's being pushed back, right? So, so this is why this would be negative in this instance, because basically F would be positive, but the displacement would be negative, right? So this is the positive number times negative number will be negative. So this is an instance of negative work. Okay. Another case, of course, you can have zero work, right? So in this case, you can see from here, well, it's possible for this to be zero if the velocities are the same. Yeah. So final velocity is the same as the initial velocity. So in this case, the energy of the box is not changing, or this could be zero from this instance, from this form, if the displacement is zero. So maybe a good example of this is if Bob is, this box is right up against the wall. Bob is pushing it, and I don't know why he's pushing it, because it looks like a pointless exercise, but he's pushing and pushing. He's going, I want to make this box move, but it's right against the wall, can't move it, right? Okay, so then this box will, of course, not move. The displacement is 0, and the work done on the box is 0. Okay, but obviously Bob is actually probably expending energy doing this, right? So this is where maybe the terminology is important. So notice that I wrote here like the work done on the box, right? I didn't really say the work done by Bob. The work done on the box is actually 0, because that's the energy that was transferred from Bob to the box, right? So that indeed is 0, because he's basically unsuccessful in moving the box, right? But he's going all red, and he's actually probably using up a lot of energy. So what's probably actually happening is that it's a little bit more like, so if we look at our bank account example, so I don't know. So Bob is pushing against the box. He's losing energy because he's trying so hard and working up a sweat. But actually nothing is going between Bob and the box here, right? So actually this is 0 because he's unsuccessful in moving in the box, right? But he's huffing and puffing, and it's getting all hot, and all that energy eventually is gone into actually heating the room. So actually Bob is doing work, but it's just not going into the box. It's going somewhere else. So that's why it's a futile exercise. All he's doing is basically being a heater for the room, right? He's just heating up the room. So if you say, how much energy is Bob using, then he actually is losing energy. But work done on the box is really this transfer there. So that's why that needs to be 0. Okay. So we can also define work in more than one dimension. So this was just a one-dimensional example. More generally, it's a vector quantity like this, and maybe this is the first time that we actually used that scalar product thing. Maybe yes. So remember that scalar product. What that means is actually, so if we have f dot d, that actually means fx, well, let's call it dx plus fy dy. Okay, I could do z as well, but say we're doing two-dimensional example like here. So when we are doing work by a constant force, and then the force is in some direction, then we can work out the total work using this. And basically it's like this because if we work out the we can just follow this type of logic. And remember, whenever we work out like these equations of motion, remember with like the projectile motion, essentially you can treat the x and y coordinates completely independently, right? So basically we can just do two parallel calculations, one for x and one for y. So also Newton's law, we also said that everything is independent in the two, or 3 directions, depending on if you're in 2 or 3 dimensions. So this is the component of the force in the x direction. This is the component of the acceleration in the x direction. This is the component in the y direction. And we again have basically the same formula, but also in the x and y direction. And then eventually we have 2 formulas that look very similar, but these are the kinetic energies in the x and y directions, and each of them are related to the force by doing force times distance, but just in each direction, right? And then eventually, if you want to say, okay, what's the total work that is done, then it is just the sum of the x and y components. So basically, we just add up that and that, right? And that's neatly summed up by that scalar product formula that we already learnt in chapter 3. So it's basically saying that the total work is just the sum of the work, individual works in the x and y direction. Okay. Because it's got this type of relation, we can kind of interpret this in a slightly more geometrical way, I guess. So if you can have a situation where the force and the actual movement are not in the same direction. Right? So an actual example would be something like this. So say you got this bead and it's threaded through a wire. So you've got some wire and the bead has a hole in it. So it's just running along this wire. And let's say you attach a piece of string to that bead, and you're pulling on the bead, but the wire is making it move in a particular direction. It can't move anywhere except along this wire. But the force itself is not along the wire. It's actually sort of diagonal to the wire. You're kind of pulling up on the wire. Pulling up on the bead at some angle like this. So this is a pretty clear example where the force is not acting in the same direction as the eventual movement. Right? The actual movement has to be along the wire. It's forced to be like that, but then the force is some direction that's at an angle. And we learnt in chapter 3 that we can work out this scalar product. So this was kind of the definition of the scalar product, right? You just look at the x and the y components, multiply them, add them together, right? That was the rule. But we also learnt in chapter 3 that there's another way of writing this, which is that we can, if we know the angle between them, we can write it like that, where this f is actually this is the length of the vector f, and this is the length of the vector d. So if you work out what the length of those vectors are, you can do that just with Pythagoras' rule, or perhaps it's just given to you. But you can work out this scalar product in either of these 2 ways, and they will both give the same answer. So this often gives you a sort of easier way of calculating. Well, it depends upon what's given to you in the question, right? But you basically choose the one that's kind of easier, right? And so because it's got this cosine factor, this basically means that, for example, if when cosine is 0, then basically these two forces are parallel to each other, right? Oh, sorry. This force and the displacement are parallel to each other, right? So they're moving in exactly the same direction. And so this factor is 1, and then you just recover basically something like what we already said in one dimension. Now, if this cosine is 90, basically then what's happening is that you are, instead of pulling it diagonally like this, you're actually pulling it straight up like this, right? Now you can sort of imagine, if you're just pulling it straight up, this is basically not really going to do anything, or, well, it's not really going to contribute to moving the bead, right? It's just going straight up. So in this case, the work done on the bead will be 0, because basically these are completely perpendicular, and essentially the force that's acting on it is kind of useless in terms of actually transferring energy. Now, if it's some angle which is say 90 to 270, so this basically means that instead of it, say the beads are always going right. Now, if the force is sort of going at some angle that's generally the opposite direction to the movement, then this will be negative, because cosine becomes negative after 90, right? So this is cosine. So it's going to be, this is 90 degrees. So after 90 degrees, it's going to become negative. 180, it's completely negative. 270, it's, well, according to this definition, it's pointing sort of that way. Less than 270. 270 is exactly pointing this way. And then when it's getting above 270, it's pointing this way again. That's why it's positive again. Okay. Okay. So this is how we calculate the work for a vector. But what if there's more than one force? So as you might expect, so it's actually just the total sum of the two forces, and you can work this out in basically one of two ways. So you can view these two forces as being, you can calculate the total force of this object, right? So just calculate the total force F1 plus F2, because we know that forces just add vectorially, right? So you add two forces and you just add the vectors of the forces, and then you have the total force. So you can basically view these two forces as one force, so to calculate the total force, and then you just do force times distance, or F dot x. Alternatively, you can view it from the point of view that, okay, well, these are, say, imagine these are like two people pulling on this box here, right? So here's person 1 pulling this way, person 2 pulling on this way, right? And eventually the box moves in some way, but after all, this person 1 is giving some energy to the box, and person 2 is giving some energy to the box. So surely the total energy that's given to the box is the energy given by person 1 and the energy given by person 2. And you'd be right. So basically, you can alternatively add the energies that are actually transferred and add them from a kind of an energy point of view. So either way basically gives the same answer, and, well, it's obvious in a way, because if you substitute W1, W2 here, then you'll get exactly the same formula here, but the sort of the mental picture that you have is a little bit different, because you sort of, in the first one, you're adding up the forces and you're viewing the whole thing as a total force. Second one, you're adding energies. Yeah. Okay. So so this is maybe one of the central results of this chapter. So it's good to get your head around it, even if you've seen it before. So we've basically already said it, but just to formulate it as a more general sort of theorem, we can put it like this. So we can say that, well, the work-kinetic energy theorem basically says that the change in the kinetic energy of the particle is equal to the net work done on the particle. So that, in a way, we've already said it. So formula-wise, that's basically all it is. Of course, you can rearrange this in this way so that, the final kinetic energy is equal to the initial kinetic energy plus the amount of work done on the particle. What's this positive work when it has an effective component? I think we've covered this. So yeah, and basically, again, the way to think about it is like this. So so what is the kinetic energy theorem saying in this instance? Basically, it's just pointing out this fairly obvious fact, which is that, so we've established that, so here's the energies of a bunch of people, or here's bank accounts of a bunch of people. We've established that work is the transfer of energy. So basically what the work-kinetic energy theorem is basically saying is that if $2 goes into this person's bank account, then the change in the money that Bob has is $2. Okay, so it's pretty obvious, right? But that's basically what the work-kinetic energy theorem is saying. It's like the work that you are transferring, that's the energy that you're transferring, changes the energy of the person, like that's receiving the work in this case. So basically these two things, that number there and the change here are equal, right? So the change in the kinetic energy is equal to the work, which is the transfer amount. Okay, so that's basically the statement of the work-kinetic energy theorem. So, it seems kind of quite obvious, but of course, it doesn't necessarily need to be like this. And in fact, what we'll see is that this is a kind of a somewhat idealized situation when there's only there's only kinetic energy and there's work and that's being transferred, but we'll generalize upon this concept later on when we'll have different types of energy. So if you've got potential energy, kinetic energy, and all these types of things, then it's sort of like having different bank accounts here. Okay, but this is kind of the central result of this chapter. So, any questions on this? Okay, so then let's do this checkpoint. So particle moves along the x-axis. Does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes, say firstly from minus 3 meters per second to minus 2? So does the kinetic energy increase, decrease, or remain the same? Decrease, right? Yeah, because kinetic energy is half mv squared, so the minus sign will disappear when you square it. Right? So this is like half m9, and this is half m4. From minus 2 to 2, does it change kinetic energy? So no. So kinetic energy, what remains the same, right? Okay, so in each situation, is the work done on the particle positive, negative, or zero? So here it's negative because the velocity goes down, yeah? Okay, here what about the work done on the particle? Right, zero. We just learned that. Kinetic energy change, zero. Work done is zero. Okay? But surely something's been done. Velocity has changed. So how do we reconcile this? How can it be that the work done is zero? Because it's like, okay, here a box was sliding towards me, and then I'm pushing on it, and I've slowed it down, and I pushed it that way. Surely I've done some work there. So how do we reconcile this?
So the negative work and positive work done on the object is the same. So when the multiply them, they'll be zero.
Right. Yes. Yeah. So that's the trick. So this all looks all like you come here and you go, yeah, it looks all very easy, trivial, and then when you look at it and you go, wait a minute, that's pretty confusing. But yes. That's exactly right. So that's how you can sort of reconcile this, because basically, so maybe it's good to draw a diagram. Right? So at first, so we've got something. It's going -2 meters per well, it's going 2 meters per second to the left, right? And so that's the initial situation. And this is the final situation. Well, okay, maybe what I'll do is so this is the final situation. And so if we're talking about the work done, and so in order to achieve this change in velocity, so there has to be some force that was going in this direction, right? So let's draw the man. So the man is pushing. So he's got some force that's always acting this way. Now, basically what's going to happen is that this thing is flying towards him this way, and, well, to sort of exaggerate the whole thing a bit, at first, there will be basically some point where he would have gone backwards a little bit. He's still applying his force. And suppose over here the velocity is 0 here, right? So between here and here, actually the work done on the system is actually negative, right? And so if we were to calculate it, find the distance, right? So basically this will be the distance here. And so the work done here, between here and here, would be basically force times distance, but with a minus sign, because the distance is actually kind of in the opposite direction to the force, right? And from going from here to here, the work done on the system will be force times distance, because this is now in the positive direction. And then when you add both of these two things together, then the total work is 0, right? So that would be basically what's happening. Yeah. And in fact, I mean, I think this will always be more or less true. I mean, we did a sort of an exaggerated situation with this box flying towards you and going backwards. You might think, oh no, realistically, I just stop it and push it that way, right? But actually, there's always a little bit of backward movement that you have to counter, because basically you can't just go from -2 to 2 like in no time, right? Like you have to go like -2, -1, 0, and then 1, and then there's basically no way, even if you apply a very large force, there's always that time when you're going backwards a little bit and then forwards. So yeah, so that would be what would be really happening in terms of the work. Yeah.
How do you know when you are pushing back the box, the displacement are the same when?
Oh yeah. Well, yeah. I've assumed that this force is constant, right? Now, if the force wasn't constant, then yeah, it might not be completely symmetrical like this. So perhaps it might be 2 meters per second here as well. But well, as we'll do in here, like if you have a variable force, basically eventually it all becomes the same thing. So this is a kind of a simplified situation, like just for this case, but eventually the work-kinetic energy theorem still should hold, even in the case that it's not symmetric like this. Yeah. Okay, all right. So I think we should go on to the presentation now if there's no questions. Okay, all right, so let's go on to the presentation.